we're from SaskTel. We're in Canada, in Saskatchewan here, and Aaron and I are part of the Telco Cloud dev team. So both of us here are, kind of come from a bit of a diverse background, but we've been working together for a long time. So primarily for myself, on the cellular core network side of things, I've been looking after PS core 3GPP networks for 15 years or so. Lots of service provider routing switching background. And Aaron, in this case, with me working in a support role and then into dev here, did a lot of the software development component of our infrastructure for a number of years. And so we kind of came together into this Telco Cloud team. And we had a lot of backgrounds in Aaron's case, a lot of sort of OG Kubernetes, which was important for us to have a Kubernetes background coming into this because with Telco Cloud and 5G, sort of a core component of that is we had to decompose all of our functions that are making up our 5G networks that traditionally have been rather metal box based here. So we currently have an OpenStack cluster that we host a number of network functions on today, and OpenShift is our choice for our container network function to deploy that on our platform. So we're I guess the primary guys that are looking after all of this stuff at SaskTel. So pardon the nerdiness that we'll get into here. So what's different about Telco Cloud and how is it the same? So basically, Telco Cloud is no different than everybody else's data center cloud. It's just the kind of workloads that we tend to run. So what we used to have is a big metal box with lots of LAN cards, lots of cables coming off of them. Those essentially have become pods or containers. So we're decomposing those functions into little purpose-built microservices, or attempting to. We have, quite important high availability requirements that sometimes I think everybody says they do and likely do, but in our case, being a service provider, we have 911 services. If something breaks in our network, we make the news. Yeah. So it tends to be we're very careful about what we do on the network when we touch it. Latency sensitive voice services, this is all your VoIP, even your traditional circuit switch voice services that are still around for some of us. Control plane, so we have a lot of complex control plane signaling that is very kind of all the call setups. So every time you make a phone call, you get an MMS, you use data. There's a litany of different control plane functions that are kind of interacting with each other to make that call work. Any one of those doesn't work, everything breaks. We have a lot of very specific industry protocols that are not very oftenly used. SCTP, diameter GTP, and we have a lot of really nascent and really terrible interfaces to manage these elements here. So MML, if those of you are familiar with MML, it's basically writing in the matrix. So in any case, with the telco, because of all these issues that we have in terms of the workloads, our change management process is really long and drawn out, and we're hoping to obtain a lot of operational efficiencies by moving to container-based services here. So this is just sort of an illustration of sort of where we were, where we're coming from. So in this case, this was like a Nokia DX200, which is a voice switch. This is what we're in many telcos across the world. This is what we're trying to get away from. This is what we were promised we were getting away from by a lot of the vendors in this space that were selling us these products. And then this is what we were expecting, right? We were expecting a data center, racks of servers, commodity off-the-shelf servers. We'd have vendors that were scattered about amongst all of this infrastructure. It wouldn't matter anymore. We just have software at this point. So what ended up happening was we got this. Every vendor that we spoke to, they approached us and they said, here's your MSS, your gateway service, your MME, your AMF. It's a box. It's a great big rack now of servers instead of the big beige box. So they basically just forklifted out beige with matte black. And so when they would come to the table with these offerings, for us, in our case, it was a 5G core network, basically, they wanted to provide us with the platform itself as well. They wanted us to use their OpenShift install, use their entire ecosystem. And so we thought, okay, let's and see what they have to offer here and deploy with what they have on offer. And so what we were seeing here was when the vendors would come, first of all, OpenShift install was manual. So they brought in their own platform, but yet none of it was prepared. It was all just servers and compute, storage, and they were doing manual OpenShift installation. They also came to the table and said there's only going to be one container network function vendor. So vendor X is going to run on this cluster, and no other vendor shall run on this cluster. That was one of the differentiators we found with some of the proposals from vendors, is that some of them were open to the idea of multi-tenancy, and some of them were dead set against it. We noticed that there was cluster admin and root access everywhere. And so when you start to pull back the curtain of what's under this box that they're trying to sell you, is they get to hide a lot of the dirty deeds that they have, that they previously were kind of compiled into some box that you never had any access to. The workloads. I mean, we've got all these container workers that are supposed to be agnostic to the workloads, and we're expecting to be able to schedule workloads dynamically, scale out, but also for operational and maintenance reasons, move them wherever we wish they would go. But what they were doing is they were scheduling workloads to a given node by host name. So we have one host. If it's dead, it's dead.
Yeah.
And somehow this was not sort of resonating with them when we were pointing out these challenges. No version control. So, you know, as it's showing here, we would get Helm charts and values in an email, just with, you know, a version tag at the end of the tarball. The configuration changes post-deployment. So you've got a platform running. This is sounding all very negative, I realize. But you got a platform running, and you're like, okay, well, let's get this CNF bootstrapped. And what happens is they exec into the pod. They vim into a configuration file within a running pod. And only because there was persistent volume would it actually retain the config after a reboot. But there was just all of these sort of very bad practices that we felt weren't representative of what real cloud should be. And so, you know, these are the things that we sort of identified that were missing from it. You know, there was no multi-tenancy, and so we wanted to achieve that. Scale in, scale out wasn't really there. Security was clearly a challenge. Automation was really nowhere to be found. Yeah. There was no CI/CD, and really, fundamentally, there was no GetUPS for the configuration of these manifests here. So this was the very first sort of epiphany moment for us when we realized something was very wrong. When they went to do the OpenShift install, they loaded up an ISO of Red Hat CoreOS Live. They pressed E on the keyboard, and they began to type in the kernel arguments into the screen from a notepad, but they couldn't copy and paste it because Virtual Console doesn't allow you to copy and paste. You have to literally type this, and it was mistyped a number of times.
And it's not a small vendor.
Yeah. And so when we observed this is sort of when Aaron and I looked at each other, crossed our cubes, and we're like, say, something has to change here. So this was sort of what we went into with our key requirements for what we were hoping to achieve, which was private cloud. So we are Telco, so all of our infrastructure is all on site. It used to be a disconnected install because of some of the security components of this, being a service provider. Least privileged security, multi-tenant cluster, multi-tenant on the same cluster, and then also multi-cluster. So we recognize that there are going to be cases where we need another cluster because that one vendor happens to have a kernel version or a very specific, you know, SCTP library that's tuned in a certain way that has to be their own cluster. So we wanted to make sure we would support that. We wanted GitUPS for all configuration. No more executing into containers to do configuration management. Node labels based on capabilities, not by the fixed vendor function. So this was meant to be more elastic in terms of where workloads could go. And then integration into our existing ecosystem. So we're very big, heavy users of NetBox, Ansible, Terraform, TerraGrunt, and GitLab, and for secrets management, Vault. So we want to tie all these tools into our deployment. End-to-end automation, we wanted one-click cluster for this whole thing, from infrastructure to running tenants inside the cluster. And it needs to be, you know, obviously replicable across those environments here. So this is where we started, was with our data modeling. So we use NetBox for all of our IP fabric configurations. So we have like a standard 3-tier Clo fabric where we do all of our VXLAN, east-west traffic, north-south for all of our interconnectivity from our workloads that are in OpenShift into our more traditional physical functions. And so because we're heavily using NetBox for data modeling for IP fabric, we thought makes sense, let's use this for OpenShift, as we already use it for OpenStack to basically ensure that all the VLANs and all the IPs and everything is modeled in NetBox. We can enable the infrastructure and the platform to run on top of that. NetBox is sort of an 80-20 tool. It's meant to sort of solve a lot of problems, but not every one of them. But it's still flexible enough here that we're able to do a lot of the OpenShift primitives and integrate that into NetBox. UI scripting. So NetBox has an ability for onboarding like a wizard-driven sort of custom scripts that you can make so that your less technically capable folks, in our case the provisioning team, can onboard new servers quickly. And it's got APIs that integrate with all of our tool sets. So what do we model? We get all of our traditional network components here that are modeled up. We classify everything into models, roles, and tags. Everything, cables, rack information, all the prefix and VLAN assignments. So a lot of the things that you're probably seeing here are what you would likely be putting into your cluster install YAML file. Rather than us doing that into manually, basically NetBox becomes our source of truth for this information. All the IP address information, so API ingress, like star.apps, your API, all that gets modeled into NetBox. And any configuration that falls outside the bounds of NetBox, we put into configuration context. So why is this important? Well, I mean, everything, the hot rage is, source of truth, but ultimately we need documentation and inventory on what we're putting in for OpenShift. So the UI is really helpful for us to get everybody on board with it. If the UI is usable, everybody wants to use it. Validating and auditing, we can run reports here. All of our cable checks, we can do our intent of where the cable is connected to a server. We can verify that through Redfish APIs to say, do the two align? We can fix cabling problems before they become operational problems. All of our IP fabric configuration stays right in lockstep with the VLANs that we need to expose towards our workers. Infrastructure as code is like, we couldn't do this without having an API to call back this data from. And so Terraform has GraphQL data source plugins that tie in really nicely with NetBox. The GetUPS component here is that as we add new VLANs to NetBox, we're able to sort of dynamically use NM state to create and expose those VLANs to our workers so that it all becomes sort of part of the same workflow. And then obviously, as I mentioned about the data modeling flexibility of NetBox is that whatever we couldn't quite do with the native NetBox data model, we found a way to achieve a similar result here. So basically, the OpenShift user provision approach is the approach we took to provision our infra. We like it because when you do the installer provision, it's great, but we didn't really understand what was going on behind the scenes. It's just a binary that runs. So we wanted to sort of pull that all back. So we brought our own DNS, we brought our own DHCP, we brought everything to the table ourselves, and we were willing to sort of run with that. So NetBox is there. Terraform is there for all of our provision of our F5 load balancers, the VMs inside of libvirt, workers, cluster, and tenant GetOps. The whole soup to nuts of everything is happening through Terraform in this case. We have modules broken up so that our teams can kind of work on separate little components of the overall cluster deployment and use semvirt to kind of keep that all intact. And then GitLab is our source control. So we have a disconnected registry in our environment because a lot of our telco vendors or tenants, they come to the table with their artifacts. And so what we have here on the left is basically different ways of traffic coming, or of the registry pulling these artifacts, either through VPNs, special tokenized public infrastructure. We throw everything into a DMZ to do scans, make sure that all the charts and or the container images themselves are sound. And then we subsequently let our security team approve that, and then it moves into our internal registry. So we don't have any internet access to this, so we basically have to mirror every single tenant VNF sort of Quay.io, Docker.io artifacts into our internal registry here. So basically, cluster one, sort of similar to the last one, we get the cluster going here. DNS, Let's Encrypt for all of the, and DNS and Let's Encrypt certs, we get that all done through the NetBox and the Terraform plugins or providers. All the secrets are in Vault. Matchbox profiles, that allows us to link the serial number of all the servers that we have in NetBox and tie that to basically the personality of that node. Is it a controller? Is it a worker? iPXE is the scripting language of iPXE has been super helpful for us. We basically can create scripts, embed it into an ISO, and we can selectively say, I'm this controller or I'm this worker based off the serial number. It knows what its IP is. It knows how to, and in particular, what's super important, if any network guys are here, LACP responder support. We do active-active EVPN. So in those cases, you need LACP responder, or you have issues with weird using a single interface to do all your PXE booting, which was a non-starter for us. Basically, then we get the VMs up. We bootstrap with Terraform to get a bootstrap controller. We spin up our VMs on bare metal hypervisors to be our control plane for etcd, and then we build the workers. Basically, bringing this all together, we have a Terraform apply, wait 10 minutes, you've got an OpenShift cluster, all with the data from NetBox here. So I'll let Aaron touch on the GetUPS here part that he's in front of.
Looks like we're short on time here, so. Yeah, I guess core fundamental of GetUPS, most people are familiar with that. Like Jerrad mentioned, we bootstrap our GetUPS approach with Terraform. All of our policies and access roles are all auto-generated at the time of our base install and our Terraform apply. For GitOps, all the repos get SSH keys, access tokens, all of that. We've written a number of custom providers that we use internally to make this sort of all work and come together. For our core cluster, we have about 30 to 40 different operators that we need to use. We chose to use most of them through the OLM operator installation, but we do that through a GitOps approach where we have a job that will actually manually approve the installation plan and then run through there and so forth. And it works great. And we've had to work around issues with failed artifact remediation and all that kind of stuff. That's all sort of taken care of there. The biggest issue, though, has sort of been the whole disconnected environment where you might use OLM to install an operator. It may use SHA, it may use tags, and in the case of tags, it's not supported. So that's a number of container or cluster restarts before we can really get going. Jerrad touched on the fact that we use nm state operator, and that's been fantastic for us. Everything is auto-generated through CI/CD pipelines for all of our VLANs, for all of our tenants, and it's worked flawlessly for us. We also use a patch operator to label every single node with its capabilities based off of the data that's in NetBox. So these are all, once again, generated through a CI/CD pipeline and webhooks that come in, labels, physical racks, all that kind of stuff, so that we can ensure affinity across racks as well. So yeah, multi-tenancy using GitUps. I'll just kind of fly through that here. We started with Argo CD, and it was fantastic. We've used it before for a very long time for some other internal clusters. But as time went on, we had vendors come to the table where they're using Helm hooks that are not supported. Not one or two, but in the order of 200 or 300 Helm hooks that aren't supported by Argo CD and never will be. Well, that's a problem for us. So, we looked around, and yeah, there was other ways that we could have accomplished some of it, but we ended up going with Flux for our primary tenant GitOps approach, and it's worked for us. Just kind of blow through this here. Actually, I'll go back here. So validation, once again, the vendors are used to hiding a whole lot of stuff in their deployments and their applications. But with the ability just to look at the templates directory and the Helm charts and actually interrogate what's going on, it's kind of really uncovered a lot of shortcomings of what's being delivered. There are things that you wouldn't see in a community Helm chart. They are bad practices all over the place. And that's kind of been a problem for us. So mono repo versus poly repo, that's a matter of opinion here, but we ended up going with a poly repo design, one per namespace, because we might have different owners for different namespaces. CNF might come in and they might need 30 namespaces for their particular application. Yep. I know. So we just found that this was just a better sort of flow for us. We're short on time here. So vendor workflow, typical approval stuff. So Apache Airflow. I'll just quickly touch on this, I guess. We use this to validate all of our VLANs and everything that's sort of gone into place. We do performance testing. It's all automated. It's all based off of NetBox. As you can see, we're really short on time here, so I'm going to just have to blow by that. So challenges. One of the biggest problems that we had using GitOps and Helm is the fact that none of the CNFs that have come to us actually have valid templates. So you run Helm template, you're getting 2 namespaces on a single stanza, API duplicated, just invalid templates to apply. And obviously, when you start using GitOps, that sort of doesn't fly. So we've had to work around a lot of this, and a lot of it has been pushed back from the vendors saying, well, just make it work, or we can fix that, but it's going to cost you money type of thing, just for best practices. So it's kind of been a problem. And we're out of time, so yeah. This used to be 60 slides, and yeah.
Yeah. All right, thanks.
Yeah, thanks.